from the CFA. Oh, good. Talking about Spindown from fully convective and dwarfs. Take it away.
Thank you. Hi, everyone. So my name is Emily Pass. I'm a fourth-year graduate student at Harvard, and today I'll be talking about my work studying the spindown of fully convective M-dwarfs using wide field binaries with rotation periods I've measured from TESS as well as the ground-based Mirth array. So the paper was published last month in ACJ, so please take a look at that if you want all the details, more so than what I'm going to cover today. Can I advance these slides? There we go. All right, so this work is motivated by the really interesting behavior of low mass M-dwarfs in the field, and in particular, their bimodal rotation periods. So what you see is that there's two distributions. There are very rapidly rotating M-dwarfs and a population of slowly rotating M-dwarfs at around 100 days. But there's not a lot of stars in the middle between these two modes. And that's telling us something about how these stars spin down. Because if spin down was a very slow, gradual process, you would see stars filling in this gap entirely. You wouldn't see two peaks. So spin down most occur rapidly. And based on galactic kinematics, it's thought that this transition happens around 2 to 3 gigayears on average. But it's an open question whether it's happening at the same age for all these stars, or if some are spinning down earlier and some are spinning down later. And this is an important distinction if you're interested in, for example, terrestrial planets around these very low mass M-dwarfs, which are the prime stellar host for detecting planetary atmospheres around terrestrial planets with the James Webb Space Telescope, as has been discussed in previous talks. So the question becomes, are all these terrestrial planets around low mass M-dwarfs bombarded by high energy environments from active stars for many gigayears? Or is there a population where the star has spun down at an earlier age, and so the planet would have had a more favorable high energy environment and perhaps is more likely to retain an atmosphere? So over the course of this talk, I'm going to build up this rotation period versus mass plot with what we know about the rotation periods of low mass M-dwarfs, and also the data that I've collected as part of this project in order to attempt to answer this question. So this is the same field data set that I showed on an earlier slide, but note that the axis is now flipped. And you see those two populations. But of course, in the field for M-dwarfs, we don't know the ages. So that's making it difficult to see how this spin down is changing with age. If you want to resolve ages, one solution is to look at clusters, like the 600 million year old Praesepe cluster. But you see here that all the low mass M-dwarfs in this cluster are still rapidly rotating by 600 million years. Now let's bin that up, so I'm going to be adding a lot to this plot. So if you want to know when these stars are spinning down, you need to look older. But it's difficult to do this with clusters because in older clusters, you need to look further away, and these very low mass M-dwarfs are very faint, so it's difficult to get the rotation periods. So you want to be able to do this with nearby field stars, but we don't know the age of the M-dwarfs that are nearby in the field. And that brings me to what I've done, which is sidestep this issue by looking at wide field binaries. So first of all, I collected the sample of M-dwarf binaries and measured the rotation periods with TESS and Mirth. And so that's this distribution I'm showing here. So with a binary M-dwarf system, you still don't know the age, but you know that both the components have the same age. And so that's informing you something about age on this diagram. And what you might see is that there's kind of 3 distinct populations here. I've color-coded in green, where both systems are slowly rotating. Then they follow that slowly rotating sequence from the field, where both systems are rapidly rotating in blue. They're kind of random. But most interestingly are these systems I've colored in red, where one of the stars is still in that rapidly rotating reservoir and the other has begun to spin down. And in those cases, you see a characteristic positive slope, such that the more massive component has begun spinning down, while the lower mass component is still rapidly rotating. So there's a very strong mass dependence on the epoch of spin down that you probably saw just by looking at that data in Praesepe. This is useful, but we still don't have specific ages for this diagram. And that brings me to the next set of stars that I looked at, which are M-dwarfs in wide binary pairs with other types of stars. So first of all, white dwarf M-dwarf pairs, where we can age the white dwarf using white dwarf cooling curves. And so those are the 4 systems I looked at. And then these are the ages that I found. So you'll see that up in the top corner, the two stars that match that slowly rotating sequence in the field are both very old, greater than 5 gigayears. The one that's at this intermediate part of the diagram, where it's partially begun to spun down, is intermediate in age, 1 to 3 gigayears. And maybe this one down here is surprising. It's rapidly rotating, it's very old, and it's high mass. And we thought that maybe this is actually a close binary, where its rapid rotation is persisting because of interactions with a currently unknown companion. And so we follow this up with high resolution spectra with trace, and we found that indeed it has a previously unknown close companion that's spin orbit coupled. So mystery solved on that one. We do the same game with our FGKM sample. So sunlight primaries that we can age through gyrochronology and lithium abundance, which we get relatively similar estimates. These are age posteriors for each of those techniques. And when we put the age on this diagram, what you see is that the 1 to 3 gigayear stars are all kind of grouped together here. So what you're seeing is that the rapidly rotating sequence from Praesepe at 600 million years has slowly begun to spin down over the course of a couple gigayears, but it hasn't made that jump to that slowly rotating sequence yet. Meanwhile, for the very young stars, less than a gigayear, you see a huge dispersion in their rotation periods. And in particular, you see this one that has already made that jump to the slowly rotating sequence by about 600 million years, which maybe is odd, because at the beginning I said that we had all this data from Praesepe when there hadn't been stars like that in that sample. But when we went back to look at the Praesepe data, what we found is that there are stars with similar masses and rotation periods in Praesepe, but they'd been missed in previous studies that used K2 to get the rotation periods, and K2 wasn't able to get such a long rotation period. So in conclusion, most fully convective M dwarfs spin down slowly, gradually evolving in the rapidly rotating reservoir over a few gigayears before jumping to the slowly rotating sequence. But a small number make that jump at very young ages, like around 600 million years. And as I mentioned at the beginning, this latter group is potentially interesting with respect to planetary habitability. So thank you for your attention.
Thank you for the nice talk. Let's have some questions. Oh, sorry. Yeah. Sorry, I'm not doing my job.
So I was considered by the slowly rotating young stars. And it was often like you win and look in Praesepe, and I was curious whether we will have plans to see if there are new populations very slow rotating stars other than clusters or other than.
So, oh yes, so the question was that it's very interesting that there's stars in Praesepe that have spun down to the slowly rotating sequence. Have we looked at other clusters to see if there's the same effect? We haven't done a systematic search, but we do have one candidate in the Hyades, which has a similar age to Praesepe, but we haven't done a systematic investigation into that.
Andrew?
Other than we show the isochronal ages, which are very uninformed for M dwarfs. If they're a member of young moving groups, of course, but then we're still getting those very young stars that we're less interested in for this question. I'm not aware of, or nothing's coming to mind immediately, but I'd be interested to discuss if you had some other ideas. Astroseismology, that is a very good one. Oh yeah, well, we already looked at this whole sample is based on common propagation pairs. Yeah.
There's a question from online. Oh, I'm sorry, we're not doing a good job of repeating comments. Dave was commenting about common proper motion pairs, astroseismology, and my apologies if I missed other comments. We got time for one more quick one, which we have online. In binary stars, how do you determine which star is dominating the signal? Yes.
Yes, so I didn't really talk about the survey design here, but I mentioned that we use TESS and we use MERTH. So for the TESS sample, we look for widely separated pairs that are more separated than 100 arc seconds, so not ones that are blended in the TESS photometry. With MERTH, which has is able to resolve closer sources, we do get some closer pairs as well, but these are all widely separated, not close binaries.
Thank you. Let's give Emily another round of applause. Okay, our next speaker is Jeremy Rigney, who is online. Jeremy, could you share your screen?
Yep. Can you see that okay?
Great. Yes, it looks really nice. Okay, I'm gonna come up and verbally give you a 2-minute and 1-minute warning. Take it away.
Okay, thank you. So thank you for giving me the opportunity to speak to you all today. My name is Jeremy. I'm a third-year PhD student with the Dublin Institute for Advanced Studies and Armagh Observatory. And I'm going to just speak about some of our recent work, which was searching for stellar flares from low-mass stars, specifically M dwarfs, using the ASKAP radio telescope and TESS. So I'd just like to quickly summarize M dwarf activity, and I like to do that using the sun as an example. So the sun's activity typically takes the form of flares, which are rapid releases of electromagnetic radiation, and coronal mass ejections, which are large releases of plasma from the solar surface. And we examine this activity across the spectrum, particularly at UV, X-ray, and radio wavelengths. And this is very important in the context of space weather, because these events have impacts on Earth. And when we look at M dwarfs, which to broadly characterize them as rapidly rotating, highly convective stars, roughly 50% to 10% the mass and radius of the sun. These M dwarfs have much higher magnetic field strengths and much greater activity, and we see this in the form of very high energy flares, which are tens of thousands of times stronger than we see on the sun. But we don't fully understand the M dwarf activity, and particularly its impact on orbiting exoplanets. So we need to examine them across the spectrum to try and better understand this. So one way that we examine solar activity is via radio emission. This is a solar dynamic spectrum covering frequency ranges of 10 megahertz to 1 gigahertz, or in wavelengths that's 30 meters to 0.3 meters, over a duration in time of about an hour. This was taken with the Irish Low Frequency Array, a radio telescope here in Ireland, and Orphée, which is a radio dish in Nancy in France. And I'd just like to highlight a couple of features on this dynamic spectrum. These bright vertical bursts, which you see in the top left corner, are called type 3 solar radio bursts. These are electrons accelerated along open magnetic field lines and can be associated with flares. But primarily in the center here, these bright radio bursts, which is called a type 2. This is produced by electrons accelerated by a shock front. And this is the clearest signature that we have at radio emission of a coronal mass ejection from the sun. We also get this type 4 sort of diffuse afterglow emission, which you can see in the bottom right, which can also be associated with CMEs. But moving now to M dwarfs, and what do M dwarfs look like at radio wavelengths like this? This is a summary of a population of M dwarfs, a study by Callingham et al. 2021. And one of the things, we're not quite sure how these M dwarfs emit at radio waves, whether some of them are radio quiet, and perhaps whether the emission mechanism is beamed. So if the beam never reaches Earth, we may never see emission from that star. But we do see M dwarfs at radio emission, and so we can examine this to better understand whether look at flares at radio wavelengths, and also if coronal mass ejections occur on M dwarfs. What I'm showing here is a dynamic spectrum in the top figure. This is work by Zick et al. In 2020. So this dynamic spectrum at the top runs from about 1 gigahertz to 750 megahertz. And what I want to highlight, first of all, is this bright vertical banding in the radio emission, which aligns with a TESS optical flare. So this is Proxima Cent that was observed with TESS and the ASKAP radio telescope, which I'll get to in a little bit. And you can see this bright radio emission corresponding to the peak of a TESS optical flare. But what you also see is this region I've highlighted in orange in the dynamic spectrum. This is a very diffuse emission, which looks quite a lot like type 4 radio emission from the sun. So this is tentative evidence for a signature of a coronal mass ejection from an M dwarf. And of course, if this is the case, this would have a large impact for any planets orbiting Proxima Cent. But as always, we need more data. We need more data. And so The aim of our research was to utilize the ASKAP telescope, its wide field of view and TESS to look for multiple M-dwarf stars at simultaneous radio and optical emission. So the ASKAP telescope, what is it? Well, it's the Australian Square Kilometre Array Pathfinder. It's 36 dishes in Western Australia that observes from 700 megahertz to a gigahertz. Our research used 700 megahertz to 1 gigahertz at 1 second cadence. And ASKAP has a 36 square degree field of view. So it's an enormous field of view for a radio telescope. And we observed 2 fields for 26 hours, 13 hours each. Just to give you a visual idea of how large the ASKAP field of view is, I've just included a full moon overlay here over one of the beam width, the full beam widths, and there's another one over there. So you can see the 36 dishes overlap in each of their beams to give you this huge field of view. And we wanted to co-observe with TESS. So you're probably very familiar with this plot here. This is the TESS, this is a TESS sector 36 map. And I've just overlaid the ASKAP field of view to give you an idea that while ASKAP's field of view is quite large, TESS is obviously enormous. And so we were trying here to observe simultaneous emission from M-dwarfs at radio and optical wavelengths. And we detected 4 M-dwarfs at radio frequencies. These are the images of them here from ASKAP. And you see there's Stokes I and V emission. This is the polarization information on these stars. This can help us characterize the radio emission. Here are some TESS light curves of 2 of the stars, and highlighted in orange is the simultaneous observing region with ASKAP. And what you'll notice is that there are no clear flare events in the TESS light curves that overlap, bar this one at the very, very end. However, unfortunately, during that very last few minutes, the noise at the radio wavelengths was far too high, so we had to discard that last bit of data. So zooming into these regions for these 2 stars, what you'll notice is that we do have radio peaks. And one of them appears to correspond to some sort of optical brightening event that doesn't match a typical flare profile, but it does require more investigation. But what you're seeing here is that we do have some simultaneous radio and optical emission from many M-dwarfs in one observation. And this is kind of what our research wants. Thank you. Our research wants to highlight. I'm almost finished actually already, so I've flown through it. So our research, what we wanted to do is in one observation, try and get this simultaneous radio and optical emission from many M-dwarfs to try and better understand their activity levels. So radio emission provides a potential mechanism for detecting unambiguous signals of coronal mass ejections, which has huge impacts for exoplanet habitability, as we know. And I would, as a message I would like you to take home, is that I expect many more of these types of simultaneous observations to take place. Because now that TESS has 200-second cadence full frame images, we have the potential to observe many more M-dwarfs with these wide field radio telescopes as well. And if you're interested, our paper is here. I've left a link and a QR code, and I'm happy to take any questions. So thank you very much.
Thank you. All right, we've got time for questions. Andrew.
You looked for radio emission first and then checked TESS. Have you done the opposite, which is look for flares and TESS indicators in the radio emission?
He says this is very cool. And have you looked for flares in radio emission and then looked for matching flares in TESS? Have you tried the opposite? Look for flares in TESS and then radio.
Yeah, so the idea was to try and search basically so we searched for all of the M-dwarfs that we could possibly detect in the radio emission, and then we found the TESS light curves that matched those. So those were all of the stars that we had simultaneous observations for in the entire ASKAP field. Not a lot of M-dwarfs unfortunately have simultaneous or have radio emission in the field. It's primarily extragalactic sources, but it would be something that we would like to do. Like when we were choosing this field of view for ASKAP, we focused specifically on active M-dwarfs that we knew had high cadence TESS data and that were flaring regularly. So we knew they'd flare a lot, but unfortunately within the observations, they just didn't flare. I hope that helped, that answers your question.
Thank you. We've got a question online. I might have misread the figure, but it appears that the rotation period in optical and in radio are different. Why would this be the case?
Yes, so that is something we looked at. So if sorry, I've closed my PowerPoint. I'll go back to this slide. So I haven't removed the star spot modulation here because one of the things we looked for was if there was this sort of modulation at the radio emission. So was there this dimming and brightening at radio emission? And that doesn't appear to be the case. So the radio emission doesn't appear to increase and decrease in brightness with star spots as they rotate on disk. That's one possible reason they seem to be disconnected. But of course, we need a lot more data to figure that out for sure.
Thank you. More questions? Yeah.
You mentioned polarization. I just missed. Did you detect polarization?
Did you detect polarization? And if so, can you say a little bit more about that?
Yes, absolutely. So I've done that again. Sorry, I'll go back to here. Yes, so at our Stokes, you can see here Stokes I and V. So the circular polarization tells us a bit about the emission characteristics, whether it's a highly energetic electron cyclotron maser process, which is generating the emission. And in two of the stars, we did see this ECM emission, which is quite common among M dwarfs, very very high energy acceleration processes occurring. And then two of the stars didn't appear to have this circular polarization, which is quite more consistent with gyrosynchrotron radio emission. So that's what it's telling us about. Now, the ECM is actually more commonly observed with these optical flaring events at the stars at high degrees of circular polarization. So highly circularly polarized bursts are more common with the optical flares in previous research. But it's, again, something that still needs to be examined more.
All right, let's give Jeremy another round of applause. Next, we have Albert Bruch talking about Novae. Albert, go ahead and share your screen.
Well, how can I do that? This way. Can you see it?
Not yet, but I think hopefully it will load in a second. Yes, we can see. Looks good.
Okay.
I'll give you a 2-minute and 1-minute warning.
Thank you. So I'm talking to you from South America, from Brazil. I suppose that I'm the southernmost participant in this meeting. Well, I first want to thank the organizers for the opportunity to present my work here, although it has nothing to do with planets. As you all know, cataclysmic variables, or CVs, are close binaries where a Rayleigh-type star transfers matter via an accretion disk to a white dwarf. In most cases, the disk is the dominating light source of the system in optical light. CVs are extremely variable. They exhibit variations on all magnitude and time scales, from nova outbursts to irregular flickering. To detect and characterize subtleties of variable properties or low-scale periodic variations, long and preferably uninterrupted light curves are required. And here TESS comes in. In its months-long, or sometimes more, almost continuous light curves, even faint periodic variations leave marks in the power spectra, even in the presence of strong flickering. And these marks are free from aliasing problems, which often haunt terrestrial observations. I will restrict myself today to old Novae and Nova-like variables, that is CVs with accretion disk in a permanent high state, different from dwarf Novae, which have disks which oscillate between high and low states during the outburst cycle. Let me start with two examples. CP Puppis is a well-known old nova. The history of its photometric orbital period is confusing. At least 6 different periods were published in the literature, all within a frequency range. TESS resolved this riddle. The power spectra of the two available light curves contain a profusion of signals in a restricted frequency interval. Only one peak, the highest in these images, repeats itself in both power spectra. If we have a closer look at the light curves and the time-resolved power spectra, we can understand what happens. In the light curves here above and below, we see that the scatter sometimes increases a little bit. These are the colored sections. The power spectra contains a continuous, strongest one, which goes through the entire duration of the light curve. I take this as the orbital signal. But whenever the light curve contains a higher scatter, additional signals close to the orbital signals appear. And these can be stronger than the orbital signature. In terrestrial observations on shorter time basis, these can erroneously be considered orbital. This is therefore an obvious example for the potential of TESS to resolve questions which are difficult to answer based on terrestrial observations only. Another example is the power spectrum of CN Velorum, which I still do not understand very well. It contains 3 pairs of signals here at low frequencies, these ones and this one, these ones, and apparently some unstable signals, which reminds us of CP puppies. Only 2 of these signals are readily explained as being due to orbital and superhump variations. I will come back to superhumps in a minute. If we have a look at the time-resolved power spectrum, we see the profusion of unstable signals here in the middle, the orbital and superhump signals here, and the higher frequency pair of signals here at the top. And here at low frequencies, something very curious occurs. There are 2 signals which change their frequency and are apparently intertwined, one crossing over the other. So far, I don't know what's going on here. Again, these details only reveal themselves in the long TESS light curves. It would be difficult to see something like that in more restricted terrestrial observations. Let us turn now to superhumps.
Minutes, Albert.
Yes? Well, this surprises me a bit, but just let me say that superhumps occur in 2 flares, 2 flavors, positive superhumps, where the period is a little bit longer than the orbital period, and negative superhumps, which with the period a little bit shorter than the orbital period. I skipped this one to go to the main slide. I performed an analysis of TESS light curves of all Novae, the Nova light variables, for which superhumps have been reported. And I found a couple of additional systems. Together with information collected from the literature, and this enabled a more complete census of superhumps than was hitherto possible. The number of known systems adds up to 45. The numbers in parentheses at the side are additional systems which are found in a survey of about 130 more CVs, which are just initiated. So these numbers are still preliminary. 29 plus 10 show positive superhumps, 32 plus 23 negative superhumps, and there are some systems which show both types, either alternatively or even simultaneously. The light curves often also contain variations on the beat between orbital and superhump periods, thus on the disk precession period. These are normally of the order of a couple of days. Often superhumps are seen at one epoch, but not at another, so they are thus normally not permanent. However, some systems have always exhibited superhumps when they were observed. Thus, in these cases, they may be permanent or at least long-lived. I'm afraid I don't have time to go to show you some examples of how different aspects of supernova present themselves as in TESS light curves and their power spectra. How much time do I have left?
You are out of time.
Okay, so let's just show at the end the references to the work which I've done, and I thank you for your attention. Thank you.
Thank you. Right, questions for Albert? I was wondering while we're waiting for a question, if you would go back to that slide that had some text about the physical mechanism behind some of the variability you're seeing. Andrew?
Excuse me, I didn't get that.
Oh, I'm sorry. Never disregard what I said. Andrew's going to ask a question now, and I'll repeat it to you.
Sure. I was wondering if the 3-minute FFI is going to help you do this kind of analysis for many more systems.
Will the 3-minute FFIs allow you to do this analysis for many more systems?
3-minute would be just about sufficient, yes. I didn't try that yet, but I just collected the 2-minute light curves, and these are quite satisfactory for this type of work.
Okay, thank
It is
you.
quite a lot of work. You know, I mentioned that I am studying currently 130 different systems, and I think it takes me about a day or more just to investigate one of these, checking the literature about that, and also and so on.
Interesting. More questions? Yes.
Have you investigated anything about the random part or the stochastic part?
Have you investigated anything about the random or stochastic part of the variability?
Not in these data. I've I published a work about this in from Kepler data on dwarf Novae, but to investigate the flickering, this is the short, random short period, short timescale variations. The time 2 minutes is a little bit too long. I would need observations on the time scale of seconds. On optical observations, I use normally 5 seconds to investigate these rapid observations, these rapid variations.
Okay, thank you for that nice answer. Let's give Albert another round of applause. Next up, we have Connor Robinson talking about accretion variability in Taurus. So Albert, go ahead and stop sharing your screen, and then
Yes,
Connor can start.
How can I do that? Well,
You got it, you got it.
Someone else did that for me.
Oh, good, it's fine. Okay, thank you. Yes, Connor, go ahead and get that full screen. Okay, looks good. I will give you 2-minute and 1-minute warnings.
Thank you so much. So today I'm going to be talking to you guys a little bit about accretion variability onto young low mass stars or Taurus stars. And this is work that I did with TESS and then some simultaneous observations from HST and ground-based observatories. So to start off with, Taurus stars undergo a magnetospheric accretion at the sort of the endpoints of their formation process. This is a process that's variable on timescales of minutes to years, but there's a whole bunch of other processes that generate variability within these systems as well, things like disk occultation or star spots rotating around. And so the primary goal of this project was to identify if TESS reliably traces accretion onto T-star stars. So can we use this to do further studies of accretion onto T-star stars? So the scenario that we're looking at here is we have a dusty disk that extends for a couple hundred AU. And north of about 0.5 AU is an inner gas disk that's mostly dust-free. This gas disk is truncated by the magnetic field lines of the star, and the material flows along these field lines until it collides with the star at a couple hundred kilometers per second. And it seized up a patch on the star, and this is the actual emissions we're observing from the accretion process. So the sample that I'm looking at is 14 T-Tauri stars in Taurus. These are taken in TESS sector 19. These were the brightest T-Tauri stars in Taurus that just basically happened to fall onto the TESS detector. Over here are all of my light curves. You can see that they're doing all sorts of crazy things that T-Tauri stars do. I've highlighted some interesting flares that have happened during it. But you can see there's a pretty wide amount of different sort of morphologies of variability. So we'd like to know if this is tracing accretion or if it's tracing some of the other processes. So to do that, we got simultaneous HST data and Lowell Discovery Telescope data, so LDT data. Our LDT data is UPVRI, and our HST data is STIS data, so contemporaneous coverage from the NUV all the way up to about 1 micron. Our HST data was for one object, Giamarica, and then our other ones were for all 14 other ones. We also got about 2 hours per night of monitoring U-band data, which traces the mass accretion rate really well for Giamarica as well. So these were our results of comparing TESS against mass accretion rate as measured through these other tracers. On the left, I'm showing our LDT data compared to our TESS flux. So on the x-axis is TESS flux, on the y-axis is the accretion luminosity. The points in green are light curves that have morphologies that have been identified as things that are typically associated with accretion, whereas the ones in purple are morphologies that are typically associated with other things. So these are things like the differential occultation or rotation. And as you can see, there's a pretty good, there typically are strong positive correlations between the mass accretion rate and the TESS flux. But if you look at the bottom right panel here, we see that there's a huge scatter in the fitted slope between these two parameters. So TESS is tracing the mass accretion rate, but it seems like it's not consistent between object to object. Similarly, over on the right, I'm showing our TESS flux on the x-axis and mass accretion rate as measured through U-band on the y-axis for GM-Ariga. And you can see that even within a single object, and each of the nights are given by the different colors. So even within a single object, we find that there's not a one-to-one correlation between what we're observing in TESS and what the mass accretion rate that we're inferring from these shorter wavelength studies. Perhaps even scarily so, we see that the slopes for some of these nights seem to be different as well. So just basically a word of caution that if you were trying to measure mass accretion rates with TESS, it works on shorter timescales, but longer timescales are a little more tricky. On the shortest timescales, we could study this with our HST data. So here are our, we can break up our NUV data into the time tag, or using a time tag mode, we can break it up into sub-exposures, and then we can plot that against our simultaneous test data. And so on these really short 2-minute timescale changes, we see, maybe only hints of weak correlations between the TESS flux and the integrated NUV flux. But the signal noise for both, or basically for both the TESS flux and the HST data is somewhat limiting. And so doing these sort of making conclusions based on this data is fairly difficult. One of the other things that we can do with our HST data, in addition to measuring the mass accretion rate, is actually model the distribution of how much of the star is covered by these accretion shocks. And so here I'm showing the model's efforts for that, where the total model is given red, the observations are in black, and then the different model components are in blue, green, and pink. Then a non-accreting weak-line T-Tauri star is shown in blue. And then the numbers here are basically the fraction of the star that's covered by these accretion shocks that we derive from this modeling. And so by doing this modeling, we can break up the amount of star covered by these shocks, and we can look at how they change as they rotate. And so here is what we did in a recent Nature paper, where we took our simultaneous TESS light curve and we compared it against this distribution of accretion columns. Thanks. And we watch what happens as it rotates. And what we found is that the peak of the mass accretion rate is actually misaligned with the peak of the TESS light curve, which makes sense because the high density columns are tracing basically UV emission, whereas TESS is tracing much longer wavelengths. And so we understand this as basically a stratified density across the surface of the spot that disappears as it rotates in front of or behind the star. We did a similar sort of analysis with our UV-VRI photometry, but it's a little trickier just because of the sparse wavelength or the sparse time sampling that we have for these. But in general, we see that as you go to shorter wavelengths, the time lags become longer, which again is in agreement with our interpretation from our HST data. And so with that, I can leave you my conclusions, but basically TESS is not a perfect tracer of accretion, at least on sort of daytime scales. It does okay on hour-ish time scales. On shorter time scales, it's difficult to probe it just because of signal noise constraints. And we can do all sorts of interesting studies with this multi-wavelength data that TESS is able to provide, since it observes for a month straight. And I'm really excited to explore more T-Tauri stars with TESS. And I'm also on the postdoc and faculty market. So if you have any opportunities, please let me know. Thanks.
Okay, can you, sorry, we're having a little bit of technical difficulty here on our hand. Okay, Andrew asked if there's a way that you could remove your signal, the accretion signatures, so that he can look for planets in these data. And he apologizes for that question.
So that would be great. But I would urge you to look at the scaling, the Y scaling on these. In most cases, these are pretty large changes compared to what we would expect for planets. So you know, for DD tau, for example, we're seeing 50% changes on the order of a couple days. The timescales is different than what we would expect for planets. So maybe you could do something like a neural network fit to try to remove this variability, since it is correlated red noise if you're looking for planets. So maybe, but I think it's going to be really difficult. And we do see evidence for things changing on short periods too, which would also kind of hamper your ability to find planets. You also have a disk in the way, so that that will also make it more difficult to find transiting planets.
Connor, can you hear us?
You can know.
I can now, yes.
Oh, okay. I'm so sorry for all the technical problems. And I noticed in your plot in the lower right hand, it looks like you have some stellar flares there. Could you briefly comment on those?
Yeah, so these were things that for our purposes were noise, and so they were removed from a lot of our analysis. But T-Tauri stars in general are, you know, active objects, and they have very strong magnetic fields. And so I've chatted with people who do these sort of more flare-related observations and research, and they seem excited about them. But yeah, I haven't looked into flares too much. I'm mostly just focused on the accretion.
Of course. Well, let's give Connor another round of applause. Next up, we have Catherine Espaillat, also talking on a very similar topic, multi-wavelength variability.
Yes, thank you. All right. And you'll see Connor as a co-author on this. So it's going to be very related, but we're not talking about the exact same thing. So I'll be talking about T-Tauri stars, but I'll be focusing on the hot spot that is formed on the stellar surface as part of the accretion process. And I'll be using multi-wavelength observations that include TESS of one T-Tauri star. And I'll be showing that the accretion hotspot on the stellar surface has a density gradient, confirming theoretical predictions. Okay, so first I'll start discussing what we find in our coordinated multi-wavelength data set. Then I'll show how we use modeling to conclude that the observed features are evidence of a density gradient in the accretion hotspot. And then I'll quickly conclude with future prospects for follow-up. So Connor just gave us an excellent introduction on accretion and T-Tauri stars. I'm going to be focusing on how we can use the UV and optical light curves to learn more about the accretion hotspot, which again is the footprint of the accretion flow on the stellar surface. So we obtained UV through optical and optical light curves over a month for one T-Tauri star, Rigney. In the next few slides, I'll show that there are two observed features. The first is a time lag between the UV and optical peaks in the light curves. And the second is a dip in the UV and the optical light curves, and both are evidence of a density gradient in the hotspot on the stellar surface. So here are the NUV and optical light curves for Rigney. From top to bottom, we have NUV fluxes from SWIFT, U prime and G prime, flux calibrated magnitudes from the Las Cumbres Observatory. Then we have TESS, the beautiful TESS light curve, and then R prime and I prime. And just a reminder, everyone knows the TESS band pass covers the R prime and I prime data. So daily changes appear in these light curves with a period of about 6 days, which is consistent with the 6.1 day rotation period of the star. And it's evidence of rotational modulation. So there's something on the surface of the star that's rotating in and out of view. And I'll show you, in this case, it's a hotspot. So there's a time lag between the UV and the optical light curves. Here, the red shaded boxes are covering the peaks in the UV and also the G prime light curves. And they're separated, the red boxes are separated by the rotation period of the star. And then these green shaded boxes are overlapping the peaks in the TESS and the R prime and I prime light curves, and they're also separated by the rotation period of the star. And you see that the optical light curves peak a day later. The green boxes are shifted by a day after the red boxes. And we can explain this with density structure in the hotspot. So material slams onto the star, it leaves a hotspot on the stellar surface. The UV emission, as Connor mentioned, traces the high density region of the hotspot, which in these animations throughout the talk are color-coded in red. And the optical emission traces the low density region, which will be color-coded in green and blue throughout. And as the star rotates, we see different density regions of the hotspot as it goes into and out of view. And the time lag in the peaks between the UV and the optical light curves, what we're seeing here on the left is the first observational evidence that we've detected this predicted density gradient in the hotspot on the stellar surface. So the second feature that I mentioned is that there's a dip in all the light curves, and it happens at the same time. And that's highlighted by the gray shaded box, and it occurs on December 23rd to 25th. There's another dip, if you notice, on December 21st to 21st to 22nd. It was only caught in the TESS data set because the SWIFT and the photometry did not overlap in time. So I'm just focusing on the gray box there. So we see the beginning of that second dip on the 23rd in the TESS data, and we trace the entire dip in the SWIFT data and the photometry. Now, Jamiroquai does not have significant dust in the inner disk. It has a big hole in the dust distribution. So these dips are not due to extinction by dust. And what's interesting is that this dip is followed by the disappearance of the UV peaks. So you see some peaks here in the UV and the U band, and then afterwards the peaks disappear. But you still see the peaks in the optical, but they're somewhat muted from before the dip. So the dip and the eventual disappearance of the UV peaks can be explained by the density gradient in the hotspot on the stellar surface, because the high density region of the hotspot is predicted to be unstable. And when it disappears, the UV emission, which is coming from the high density hotspot, the high density part of the hotspot also decreases or just disappears. So now we can compare our observed light curves to MHD simulations of accretion, and the MHD simulations predict a time lag in the light curves between the different wavelengths, and also that the high density light curve peak should drop. So here we're using the 3D from MHD simulations of Marina Romanova. Here's a 3D view, a side view, and a top-down view. And then here's a resulting hotspot. It's crescent shaped, bent around the magnetic pole. It has a density gradient. And here are the light curves from the simulations of the hotspot. The low density region of the hotspot dominates the optical emission, and that leads to the solid line. And the high density region of the hotspot dominates the UV emission, and that leads to the broken line. Both light curves are modulated by the stellar rotation period, so that's what's giving you the peaks. And the high density region of the hotspot rotates out of view, which leads to a time lag between the light curves where the UV is peaking before the optical. And you can see this more clearly at 3P star, the period of the star, where the red is peaking before the green. And then also the dotted is peaking before the green, and also at 5P star. Right, so again, this is because the high density part of the hotspot, oh, and I'm sorry, you also see that the high density region, the red broken light curve, disappears, the peak disappears around 2 and 4. And this is just reflecting that the high density part of the hotspot is unstable. And then the right panel here, these graphics here are focusing on this peak here at 3P star. And I'll just let you go through it by eye, but 2.6P star is the leftmost, 3.22 P star is the rightmost. And as the spot rotates in and out of view, that leads to the light curves that we see. Very quickly, where do we go from here? I'll quickly describe what Ulysses and Odysseus are. So Ulysses is an HST director discretionary program to obtain UV spectra for pre-main sequence stars and high mass stars. It's the largest HST program ever executed at 1,000 orbits, and half of that is for T Tauri stars, and 100 orbits in particular is to monitor 4 targets for variability, One of those 4 targets is GMRID. And these 4 targets, some of the HST data is being coordinated, was coordinated or is being coordinated with TESS. And the data for GMRID finished coming in at the end of this year, and we will be using it to follow up this work. And then very quickly, the Ulysses program is so important that it has unified the T-Tauri star community into a team called Odysseus. Our team is made up of about 100 young star experts from around the world, and we're working collaboratively on the Ulysses data set. And our team goals are listed here, and we published our first results earlier this year. So to summarize, the observations confirm the theoretical predictions of a density gradient in the accretion hotspot, and they demonstrate the insights that we get from coordinated multi-wavelength observations. And stay tuned for more in the field of accretion and T-Tauri stars with Ulysses, Odysseus, and the coordinated TESS data. Thank you very much.
Thank you. We've got about 2 minutes for questions. Yes, Michael.
So the plus something good with kind of quality metric things for me for my and it was a little confused how that means to a time delay as it was the broadening or widening. So I'm wondering if you could say more about where the time delay is from.
Okay, so Michael asks about how the spots looks kind of blobby, but might have been symmetric about some vertical axis. And why does that lead to a time delay instead of sort of like a broadening in the light curve?
So I'll show this because maybe this one helps illustrate that. So since this is very, the high density region is very unstable, it's not expected to be symmetric. So for example, here you see that the high density part, the red part, is off shifted to one side of the entire crescent shaped hotspot. And so the red part, the high density part, can come, sometimes it's in our field of view and sometimes it's not. But the other part of the hotspot, the low density part, is actually larger. So it covers more surface area of the star. So that's why we can get that the emission from the UV, which is tracing the high density part of the hotspot, peaks first, because it's leading as the crescent shaped hotspot is rotating.
So it's not actually symmetric.
So it's not actually symmetric.
Correct. It's not symmetric.
Thank you. Make it quick.
If you could talk, can you say something about the limits that you've been able to put on the actual density gradient in like physical units, how much density and temperatures are changing across the spot?
David says really nice talk. Can you put limits on the density gradient and other parameters across the spot?
The actual
Temperature and density gradient across the spot.
Yeah, so in the paper, I don't remember the numbers off my top of my head, but we did look at that in the paper. And so we can put some limits. Overall, we find that there's good agreement between what the theoretical, what the MHD simulations predict and the observations. And I did not mention that Connor showed this, there's HST spectra that were taken at the same time as this. So there's another data set that is also consistent with what we see. So with all the data sets, we can get information about the density and the temperatures of the hotspot. And they are surprisingly consistent with the simulations, which are, very advanced 3D MHD simulations.
All right, thanks. Let's give Catherine another round of applause.
Thank you.
Next, we have Anna Payne, who's going to talk about some extreme nuclear activity. Okay, looks good. Take it away. Oh, wait.
Was it all good?
Now it looks good.
Okay, great. Thank you so much. So hi, everyone. My name is Anna Payne. I am a final year PhD student and also currently applying for postdocs. So today I'm really excited to talk about my work on the discovery that Accretion undergoes periodic flares, which we currently think are most likely due to a repeating partial tidal disruption event, and how TESS really provides us with this really detailed view of these flares. So black holes and their surrounding environment at the centers of galaxies are a prevalent source of transient phenomena. If we take a look at any normal AGN light curve, it's typically characterized by this stochastic behavior. And this variability itself is extremely interesting. It's helping us understand AGN and accretion onto black holes through this variability. I developed a large sample of highly variable AGN observed by the Assassin survey, some of which I'm showing here. And one of these objects in this sample was very unusual. The light curve for this object is completely different. As opposed to the purely stochastic behavior we expect for a normal AGN. Instead, there are these evenly spaced flares that have been detected for the entire duration of the Assassin light curve for this object, so spanning 8 years now since 2014. And there are missing flares due only to seasonal gaps in the light curve. And I'm calling this object Assassin 14KO because back in 2014, one of these flares was detected and reported as a new transient discovery. At that time, it was classified as a possible supernova very close to the nucleus, but we now know that this was not a one-time event due to explosive origin, and instead they are recurring events. And so analyzing the timings of the peaks of each of these flares observed by Assassin shows that it's very well fit by a periodic model with a period of about 115 days and a period derivative that is small but negative. So indicating that over time, the mean period is getting shorter, but only a very small degree. And the flares are very consistently characterized by a rapid rise to peak, followed by a shallower decline. And these flares are also detected in the X-ray and the UV. So as revealed by Swift, the UV mimics very closely the optical behavior. So this very rapid rise and shallower decline, but the X-ray behaves completely differently. As opposed to a brightening, the X-ray is actually dim. On very similar rapid timescales of about 4 days. So we currently think that Assassin 14KO is most likely a repeating partial TDE. And so this animation is in general showing what we believe the system to look like. So for normal TDE, the star gets too close to a black hole and it gets completely torn apart and destroyed. So it's a one-time event. But in a partial TDE, the star survives the encounter because it's on an orbit with the pericenter outside the tidal radius. And so the star is not completely destroyed. Only a fraction of its total mass is stripped. And if the star is on a bound orbit, this process keeps happening with each close approach. So once every period cycle corresponds to one flare. And TESS provides us with the most detailed look we have of these flares. One complete event was captured during sectors 3 to 5, and again during the extended mission during sectors 31 to 33. And note here the scatter is larger because of the 10-minute cadence. So this puts us in a really unique position to compare flare evolution in a highly detailed manner for 2 flares that were separated by 2 years. So overall, we're seeing, the same general behavior, rapid rise and general, smoother decline. But there are still slight differences that we could not tell from the ground-based data alone. Specifically in 2020, the rise took about a day longer to rise to a fainter peak, and the decline was much more flat compared to the decline 2 years earlier. But a commonality is that both times the flare was very smooth. There's essentially no small scale variability superimposed on top of the flare itself. And TESS was really crucial here because this was not unambiguous with just the ground-based data alone, given the level of scatter we have in the Assassin data. And this very smooth evolution is very similar to what we see for other TDEs. The first TDE that was observed by TESS is Assassin 19BT. So note there's a big difference in the timescales here. As usually with what we see with TDEs, 19BT declined over 100 over 100 days versus the very rapid event of assassin-14 KO. So if we arbitrarily shrink down 19 BT to the timescale of 14 KO, the shapes are actually astoundingly similar. But again, the main takeaway here is that both are showing this smooth evolution. So what's really important and what we can do with TESS is to measure the early time rise for TDEs. And this is something that's really hard to do because TDEs have to be discovered very soon, and then you have to be very quick with triggering follow-up observations. And so what we see with 19BT is that there's a t-squared rise. And so there's only 3 objects in total for TDEs that have this early time measurement. And they're all consistent with a t-squared rise, which is what we would expect for a simple outflow expanding at a constant velocity. But we don't see this for 14 KO. Instead, it's more consistent with a linear rise. So maybe this is due to the fact that it's a partial TDE, compared to the 3 other total TDEs. There's less mass being disrupted for each passage. But this is really illustrating why we need more early time rise measurements for TDEs. This is such a small sample. So where does this leave us? It's continuing to surprise us. After years of the flares being very consistent with the peak luminosities, last year we started to see really dramatic changes. The first indication was in July of 2021, where it was the weakest flare we had seen before. And then earlier this year, it was the brightest we had ever seen it. On top of that, the overall quiescence level appears to be brightening. So in the thinking about it as a TDE, seeing higher luminosity would indicate more mass is being stripped off. But this is something we have to just keep an eye on and see how it continues to evolve. So again, where does this leave us? Unfortunately, when I check the TESS viewing tool, it will not be observed in year 5. So hopefully during another Southern Hemisphere scan, we'll get lucky again. But again, I'd like to reiterate that one of the most exciting aspects of this object is that we know very precisely when these future flares will occur. The latest flare is actually currently ongoing. This is the most recent assassin light curve. It's currently in its declining phase. I'm continuing to study the system, so stay tuned for more. Thank you.
Thank you. We have time for one question. Yes, Michael.
Can you say more about the period?
Can you say more about the period derivative and any insight into the physics causing the decay?
Yeah, so we do, I'm going to go back to the slide. So the fact that we're seeing a negative period derivative kind of indicates that, the flares can't last forever. Over time, this would result in the mean period going to 0. So that's one thing. Also, in general, the fact that we're seeing the specific order of magnitude for a measured period derivative was actually an order of magnitude larger than the expected period derivative for for a supermassive black hole binary system. So it actually helped us try to see if it was that type of system or not. But in general, this is kind of indicating some stochasticity in the orbit of the star, how it's imparting some changes after each close passage.
All right, let's give Anna another round of applause. Okay, last but certainly not least, we have Jason Hinkle to talk about AGN.
Okay, just let me share my screen. Does anyone see that okay?
Yeah, that looks great. Take it away.
Great. Thanks so much for that introduction. I'm happy to talk today about some work that my RU student Lena Treiber and I have done on revealing AGNs using test data. So Anna just gave us a bit of an introduction to a very extreme example, but in a more normal case, as she talked a little bit about, AGNs are just accreting supermassive black holes that are slowly eating mass from their surrounding regions over time. In some special cases, like for instance, Poveghi and M87, we can get very detailed insight into the central supermassive black hole and measured properties. And a handful of other nearby galaxies, we can also resolve either stars or gas and get constraints on mass and other supermassive black hole properties. But obviously in many, many more examples, we only have indirect evidence of supermassive black hole activity. We want to understand things through sources of, for instance, optical photometry like TESS, which probes the accretion disk, and therefore we can understand both the accretion physics, but then of course how supermassive black holes are growing over time through their accretion. So we showed a little bit of this, or Anna showed this in the last slide, but of course AGNs are characterized in the optical by their stochastic variability. So on the right, I'm just showing an example of the well-known AGN NGC 5549 with light curves from the far UV to the I band, which is obviously comparable to TESS. And as you'll note, of course, all of them have this very sharp stochastic variability that's much different than the periodic variability you'd expect for, say, an exoplanet transit or a variable star or something like that. And it happens on the time scale of a few days, in this case, up to a few weeks. And obviously, this is a strong sign as compared to a normal galaxy that's just made up of stars and should have no strong variability, that if we see variability come from the nuclear regions of galaxies, it's a sign that you have this actively accreting black hole or an AGN. So all of the stuff I'm talking about today using TESS builds on work in the past decade or so, both from ground-based surveys, but also other space-based missions to select these AGNs through their variability signatures. But one of the most interesting things that we found as we've looked at AGN and their variability is this correlation shown by Colin Burke last year in a nice paper that put together a lot of AGNs over a wide range of mass shown on the x-axis here, and then their characteristic variability timescale on the y. And as you can see, there's this nice correlation spanning many orders of magnitude, but you'll probably notice that many of the objects that we have these constraints for are somewhat more massive, maybe a few million solar masses, up to even a few billion. And the timescales for these objects are in the neighborhood of a few tens to even hundreds of days. So these are well matched to the ground-based surveys I talked about before, and we can get very nice constraints on their variability. But as you start to go to this lower mass end, where you expect timescales of only a few days in some cases, this is really well below the typical cadence of these ground-based surveys, in most cases 3 to 5 days or so. And you're really not sensitive anymore to this variability. You might be able to select them, but you really don't have the cadence to kind of tease out this variability signature and get a lot of the detailed physics. So of course, this is where TESS comes in with these beautiful light curves starting at 30 minutes cadence for the FFIs in the prime mission and getting even shorter in the extended missions. And then a month long in the shortest allows us to get up to somewhere in the neighborhood of a few days, up to maybe 10 days. And as you can see, of course, there are few objects populating this lower box, maybe around a million solar masses or less, that we would expect this type of variability. So that was kind of the impetus for this study that Lena did. Essentially, we selected two main subsamples, about 140,000 galaxies from Hyperlita across several sectors selected for lower scattered light, and then specifically 6,000 galaxies from the GLADE sample that were selected to have estimated black hole masses below about 1 million solar masses. And so we collected FFI image subtraction light curves of all of these, tried to remove as many sources that were obviously contaminated by stars. And then what she did was she first selected a sample of sources to go into visual inspection by plotting their standard deviation versus their magnitude here. For the fainter sources, meaning I magnitudes or TESS magnitudes less than about 13th, we selected only the top 10% most variable, because here we're not necessarily looking to be necessarily complete, but we're looking for sources that have clear signs of variability that we believe are truly linked to AGN activity. And then as the statistics are a bit worse on this high mass end, we selected all of the uncontaminated sources to go on to our visual inspection phase. So talking a little bit more about the light curves, I mentioned these are image subtraction. Primarily, these came from Michael Fajnau's pipeline. But when we had things that we looked in visual inspection and thought they were candidates, we also grabbed Patrick Valley's pipeline, which is a little bit different. Rather than using the whole FFI, it takes 750 pixel cutouts on the source of interest. So potentially handling systematics in a bit different way. So on the right, I'm showing one of our most interesting candidates, NGC 4449, which is a very nearby dwarf galaxy and only 6 megaparsecs. And as you can see, there is this very clear short-term stochastic variability that is indicative of AGN activity. Of course, the two pipelines agree quite well in general, but we do note that, of course, near the beginning of the sectors and the data downlink, there are some disagreements which might be indicative that there are still some systematics that we need to take into account. So what we did for all of our candidates was not only did we look at this PSF photometry that comes out of the image subtraction pipelines, but we even broke it down to the individual pixel level. So here on the left, I'm showing the light curves centered on NGC 4449 here with the central pixel in black, and then moving one test pixel away in each direction. And as you'd expect, the signal is strongest here in the center. And as the test pixel response function falls off, you get lower and lower variability all the way to the edge where you have no variability anymore, which indicates that we can be more confident that the variability here is truly located in the nucleus and coming from likely an active galaxy here. So after putting all of this together, looking at all of our light curves that passed our cuts and doing visual inspection, we were left with 29 candidate AGNs. Of these, about 2/3 either were known in the literature previously or would have been selected through some other more typical AGN selection method. But of course, this indicates that potentially, similar to other studies in the past, we're finding a significant fraction, some tens of % of AGNs that are selected through variability, but not other means. And then, as I mentioned at the very beginning, we're looking for low mass black holes. So we do find quite a few candidate AGNs in these dwarf galaxies shown here with masses less than 1 million solar masses or so that are obviously strong candidates for follow-up. Although I should note, even though we're not necessarily sensitive to the detailed variability characteristics, we're still doing a pretty good job at selecting these more massive black holes as variable in the first place. So where do we go from here? I'll wrap up quickly. Basically, one is to look, we only looked in the prime mission for this paper, look at more sectors. Basically, we get faster cadence. In this case, I'm just showing the second sector for NGC 4449, which again shows us short-term variability. And then to access longer term variability and more massive black holes, we need to focus a little bit more on doing robust sector matching between the various test sectors when you have back-to-back data, which will allow again, for longer term variability, and then especially targeting sources in the continuous viewing zones. So with that, I'll leave my summary and point you toward Lena's recently submitted paper for any more details. I'm happy to take any questions.
Thank you, Jason. All right, questions? Yes.
Really nice talk. Was there any, did you see the correlation between the mass of the galaxy and the mass of the black hole?
Really nice talk. Did you see any correlation between the mass of the galaxy and the mass of the black hole?
Yeah, so I should mention, of course, measuring or estimating black hole masses is particularly difficult. So none of these are directly measured, or very few. Basically, we're taking either the best estimate available in the literature, either from velocity dispersion or something like that. But in many cases, we're just taking host galaxy scaling relationships to estimate the black holes. So that's clearly a direction of future research, is to basically take these candidates and try to measure a better black hole mass than just taking some sort of total stellar mass estimate from the photometry and using a scaling relationship to estimate the mass of the black hole.
So you mostly just scaled off the mass of the galaxy?
A lot of our sources, so I can go back here. As you can see, a lot of our candidates are these brighter ones. So they most of these have better measurements, either some sort of stellar velocity dispersion or something. So it's still scaling, but some of them are a little bit better than just like a total stellar mass estimate. But yeah, a lot of them come from scaling just because, as I mentioned at the very beginning, it's particularly hard to get resolved stellar velocity dispersions or something like that and actually probe the black hole masses directly.
All right, thank you. Let's give Jason another round of applause. All right, thanks everyone in this session.
We received more proposals for 10-minute talks than we were able to accommodate in 2 days. So I have scheduled a science team number 30, which will be science only, 10-minute talks only. But instead of 2 days, it will be 2 hours, and it'll be completely virtual over Zoom. On the 8th of December at 2 p.m. Eastern Time. And I would encourage GI Science to submit proposals to present their science at that meeting, and we need to talk about how to advertise that to GI people. I want to encourage more reports from GI scientists. And we already have half a dozen talks scheduled from that, the overflow from this meeting. So if you're interested, send me an email, dlatham@cfa.harvard.edu, and we'll try to fit you in. George, did you want to say anything?
Yeah, just a couple of things, David. So first of all, I'd like to really thank everyone who went to the trouble of making the trip here. For many of us, this has been one of the first meetings since we've been able to emerge from our post-COVID lives. And I think this has been a very good meeting in terms of the level of exchanges that we've had. And of course, one of the questions is, would we like to do this again? And I hope the answer to that's going to be yes. We would probably carry this out in the sometime early next year in this same forum. The meeting that Dave was talking about would be online, for a couple of reasons. December 8th is not a really auspicious date for a meeting in this part of New England. The other thing is that I think that it would be great for the meeting in early next year that we sort of come a little bit more toward the non-exoplanet part of the TESS universe, and so we certainly hope that people step forward with talks of that type. And I'd also like to remind everyone that we are looking for these 2 new postdoctoral positions at MIT, and so if you are interested or you know of colleagues who are interested, we'd love to hear from you. And for me, there are sort of 3 numbers to take away from this meeting. There's the number 100, there's the number 1,000, and there's a number of 6,000. And I think it's pretty clear what those 3 numbers are. And I think as we move into the full portion of extended mission 3, those numbers are going to continue to climb in a perhaps more predictable way than they did in the mission up to now. So I wanted to thank everyone who went to the trouble of coming here, and the folks online who stayed up late or got up early in order to be part of us. And so again, thank you. Thanks to Dave. Thanks to Avi. Thanks to Daniel for all the work that they did to make the meeting work as it did. And thanks to everyone here. So we'll see you next time. And everyone have a good trip and home.
I see my kids.